So this will just be a fairly short video that hopefully gives you a bit of an idea about um, physical properties and how you explain these physical properties using your prior knowledge. And basically that prior knowledge is your knowledge of things like bond polarity and molecular polarity, uh, your knowledge of intermolecular forces, and your knowledge of molecular geometry and how all of these things are going to contribute to how molecules interact either in a pure substance, so that's the same type of molecule interacting, or in a mixture, so that's when we have solutions. And so we'll go through a few of these things in this video. So first of all, just in terms of physical properties, just what are these physical properties? Well, you probably have an idea about some of these things. So properties of a substance like boiling point, that's an important one. We're going to talk about that one today. Melting point, pretty much the same as boiling point. Hardness, brittleness, those are kind of the same, and we typically don't talk about hardness and brittleness in molecular compounds because they're neither very hard nor brittle, most of them anyway. Malleability, again, that's typically discussed in terms of metals. Ductility, similarly. Solubility, for sure, we can talk about with molecular compounds. Surface tension and vapor pressure, those also are useful to think about in terms of molecular compounds, but we'll not cover these here today. So let's just look, we're only going to concern ourselves with a couple here, so these are the ones you want to be able to try to talk about rationally. And so the first one is boiling point. So just have a quick watch of this. Okay, well, that was pretty neat, I think, but it does give you the idea what boiling is about. Boiling point then is basically a temperature at which a phase change occurs and that phase change is obviously from liquid to vapor. And we know a little bit about boiling point already. We know that water boils at 100 degrees Celsius under standard conditions. So, and we do know that, I hope we know that water, this is pretty high for a molecular compound, for sure. Such a small molecule. So water is considered to have a fairly high boiling point, and we'll see reasons for that in a moment. Okay, so the other one is solubility. And so again, solubility basically is defined as the ability of a substance to dissolve in a solvent. And by dissolve, we're basically talking about interact. And that solubility varies greatly. And it varies because of the type of intermolecular forces. And that is for both the solute and solvent. And you've heard this term like dissolves like. And that really nicely sums up sort of why things are more soluble in certain substances. If we think about like dissolves like, we look at something that is polar, like water. And water, being a polar solvent, will readily dissolve other things that are polar. But that, again, varies quite a bit. If we have something, a small molecule that is polar, like an alcohol, it will dissolve readily in water. And that's because water has an OH group and alcohols have an OH group. And so water and alcohols can form hydrogen bonds with one another. So that's one of the reasons why like dissolves like. They form the same type of intermolecular force. So nonpolar solutes will dissolve readily in nonpolar solvents because they're forming intermolecular strong dispersion forces between them. And we saw this in evidence when we did our organic lab with aqueous bromine. So here's my bromine. And so the top phase, if you recall, is actually the alkane, the cycloalkane with dissolved bromine. And it's dissolved bromine because the alkane is nonpolar and bromine is nonpolar, and so they dissolve, they interact quite readily. The intermolecular forces, the dispersion forces, are quite weak in alkane, and so bromine can interact with them and form a relatively strong interaction, even though they're dispersion forces. What we have down here, if you recall, is water. And so water does not dissolve in the alkane because it interacts via hydrogen bonding, and so the alkane there's not enough energy associated with the alkane to break those strong hydrogen bonds in the water. So the hydrogen bonds of water remain intact. The alkane then cannot dissolve. Now you can dissolve it a little bit. If you agitate the water a lot, you would probably get some alkane into solution, but under normal conditions, and when we did this we just sort of poured it in, that wasn't sufficient amounts of energy to get the alkane dissolved. And even if a little bit of it dissolved, it probably came in a solution pretty readily because this hydrogen bonding in water would be stronger. Okay, so here's what you need to be able to do with the physical properties. You have to be able to, using your abundance of knowledge and all those things I mentioned earlier, be able to explain certain behaviors, certain data that you're given. And so here's a good example. This is a pretty common graph. You see it quite often. And so we want to be able to use this graph, and we want to explain the variation in boiling point for the group 4 hydrides. And the group 4 hydrides is this graph right here, that blue one at the bottom. And so we need to discuss why there's that variation. And this is pretty straightforward, but here's what we have to go through. Here's the process. Determine bond polarity. So in this case, if we looked up electronegativity, all bonds are nonpolar. And so all molecules, therefore, are nonpolar. And that's for all of these 4 different molecules we're looking at. So that's the first thing you have to look at, is polarity. Now, since there's no polarity in the bonds, there's no polarity in the molecules. And so we're looking at, as an intermolecular force, we're looking at dispersion forces. So those London dispersion forces, the LDFs, are weak. And so the boiling point increases up the group, or up that, as you move from methane, CH4, down here. This is methane, up to, that's silicon, germanium, tin. The reason that boiling point increases is due to increased molecular mass. Or size of the atom, or number of electrons. And so again, you should recall that dispersion forces are brought about because of unequal distribution of electrons. So the more electrons there are, the greater potential to exhibit or establish those instantaneous dipoles. And so that's a pretty straightforward. The boiling point increases because the central atom, that group 4 atom, is getting larger as we go down the group. Okay, well, how about explaining the variation of boiling point for the group 6 hydrides? So that is shown down here. And so we're starting at the top here. This is water up here, and then you see this big decrease in boiling point, and then you see a gradual increase again. So let's look at the gradual increase. First of all, if you look at those molecules, H2S through to hydrogen telluride, they're all nonpolar molecules. And so the increase in boiling point is the same as what we just talked about. It's due to the increase in weak LDFs, London dispersion forces. Since they're nonpolar, that's the only intermolecular force present. H2O, on the other hand, is polar, and that's due to an OH bond being polar and the orientation of those polar bonds, the shape. So it's bent. And so that bent geometry is an asymmetrical geometry, and it will give rise to polarity in the molecule if the bonds are polar. So H2O is polar due to that bond and the orientation of molecules, and therefore, and because it's OH, you get strong hydrogen bonds. So hydrogen bonding is the strongest intermolecular force. And so the hydrogen bonding between the molecules means it's harder to separate them. It's harder to break them apart, which would constitute going from the liquid to the vapor state or boiling. So that trend we just explained can also be used to explain the trends in the two graphs below, starting with hydrogen fluoride. So hydrogen fluoride, like water, exhibits hydrogen bonding, but the other molecules in that group, hydrogen chloride, and hydrogen bromide and hydrogen iodide, do not exhibit hydrogen bonding. But again, hydrogen iodide has a higher boiling point than hydrogen bromide, hydrogen chloride, because the iodine is a larger atom. So those, and the same stands for the ammonia trend. In the ammonia, pH3, ASH3, and antimony H3, SbH3. Okay, so that's one trend you need to be able to explain. Now, what about the boiling point for period 2 hydride? So now what we're doing, as it showed on the graph, is we are moving down the group. So we're going from water, hydrogen fluoride, ammonia, methane. So let's talk about methane first. So methane is not too hard to explain. Methane is nonpolar. And so in terms of interactions, it's LDFs only. That's weak. So you can look at methane as just spinning about. They don't form any interactions with one another. The forces they would form are so weak that as to be basically non-existent. So methane, not surprisingly, is a gas at room temperature. Now we do know that ammonia is polar. The ammonia molecule is made up of nitrogen-hydrogen bonds. So an NH bond is a polar bond, and that's actually hydrogen bonding. And so they're going to establish relatively, compared to dispersion forces, relatively strong bonds. And when they do that, you get these hydrogen bonds between molecules. And so now we can see here, all of these are hydrogen bonds. And so hydrogen bonds are certainly stronger than dispersion forces. And you notice that basically a hydrogen bond forms between a lone pair and basically an electron deficient or quite polar in the positive sense hydrogen atom. So ammonia actually can form 4 hydrogen bonds within molecules. But the delta En here is pretty low. It's not very high. And so while it does form hydrogen bonds, they're fairly weak. And so that's why ammonia actually has a lower boiling point than hydrogen fluoride. And we'll see that in a minute. But that said, ammonia does form hydrogen bonds. That's why it's going to have a higher boiling point than methane. Well, how about the last two? Well, let's talk about hydrogen fluoride first. So hydrogen fluoride, again, is quite polar. Delta En is large, and So it's going to form hydrogen bonds. The problem with, well, not problem, but the point about hydrogen fluoride is it only forms one hydrogen bond from each of its sort of termini. So we do get hydrogen bonds, but it's not like ammonia. It can't form multiple hydrogen bonds within molecules, so each molecule forms a hydrogen bond, delta positive component to a delta negative on a neighboring molecule, and so it can do that 2 times. That said, because the delta En is so large, that dipole, that bond dipole is quite large, and that's what's enough to make the boiling point of hydrogen fluoride higher. Now water is the highest, and what's the reason for this? Well, again, water is, as we just talked about, an OH bond. That's a reasonably large delta En difference too, so it's kind of in the middle. It's not as large as the hydrogen fluoride delta En, but it's larger than the ammonia delta En. But why does water have such a high boiling point, so much higher than hydrogen fluoride? Well, the answer is because it can form 4 hydrogen bonds per molecule. So it's like ammonia in that regard, but those hydrogen bonds are stronger because the delta En is larger. So 4 hydrogen bonds between neighboring molecules gives each water molecule 4 hydrogen bonds. And so that is why the boiling point is so much higher. And so that explains the trend this way on this graph. Now, just one more to look at, and that's solubility. So we look at, here's water, all this red conglomeration of molecules, and here's some methane. So methane is insoluble in water. And why is that? Well, methane's nonpolar, so that's the main reason. So methane cannot interact with water very strongly. So it is kind of moving around, it's striking the sides of a container of water or something, but it doesn't form any interaction because the hydrogen bonds in water are so strong. Remember, water is hydrogen bonding. And the hydrogen bonds are strong, and so the methane does not have the capacity to essentially disrupt a hydrogen bond in water to form a bond. And if it did form a bond, it's going to be pretty weak, and so the hydrogen bonds in water could reestablish themselves fairly quickly. Well, what about with ammonia? So ammonia is soluble, and again, here's the reason. We already saw that ammonia has the capacity to form hydrogen bonds, and so it forms hydrogen bonds with water, and so it's going to be able to form these hydrogen bonds with water molecules. Now it has to get in amongst the water, but if it does, it's going to be able to form hydrogen bonds. And so those hydrogen bonds get established again at the hydrogens and the delta, the lone pairs on the oxygen. So lone pairs on oxygen of water interacting with the hydrogens of ammonia. And so ammonia is reasonably soluble in water, and that's the reason. Now, so physical properties in molecular compounds, you have to consider the geometry and you have to consider the polarity. Those are going to tell you what type of intermolecular forces you have at play. And then once you establish what type of intermolecular force it is, based on strength of intermolecular forces, you can make a pretty good prediction about whether things are going to be soluble or not. You're going to be able to make a pretty good prediction amongst types of molecules and their relative boiling points compared to one another. And so that's what you need to be able to do to logically discuss the physical properties of molecular compounds.